look this up online. Good morning, this is AP Chemistry here at Spain Park. Today is Thursday, October the 22nd, which means that tomorrow is what national holiday? It is Mole Day, 10/23. Now, we are not going to be doing any kind of special projects. You're not going to have to sew a mole. You're not going to have to bake a cake in the shape of a mole, because all of those things have nothing to do with the chemistry mole. Okay? None of you could bring in a mole of donuts. None of you could bring in a mole of anything. Okay? It is nice to understand the concept, but that's something we've done before. However, if anyone would like to bring in donuts, or a cake of any kind, or cookies, or something to drink, or coffee, or whatever, tomorrow would be a great day to kind of just celebrate the magnificence of 6.02 times 10 to the 23rd. So Mole Day goes from 6.02 times in the morning a.m. to 6:02 at night. That's how we celebrate on 10/23. Okay? So, again, feel free, not mandatory, but you're welcome to bring in food, you know, and then we'll just set it out and we won't pass it out. Everyone can grab their own because nobody can touch anything the same in these COVID-19 days. Okay? So, Mole Day tomorrow. So, coming back to this. Write the equation for the ionization of atomic fluorine. Anybody that didn't look this up, bet me a nickel you got it right. There were a lot of questions on this in the other class, and you guys didn't ask me any questions. Matter of fact, I don't think you guys spoke a word yesterday. Okay? I mean, it was very low energy. It was definitely a hump day. All right. Nobody has the confidence. And can you make sure that that points this direction, please? Best you can. I hate to erase that. I love that diagram.
I don't know how to.
Are you just going to hold it?
Do I move the whole entire stack of books?
Yeah, just kind of twist the books.
This is about to fall on the floor recently. Oh no. Oh no.
Sorry, you at home, you're getting high quality video here. Alright, so for the ionization of atomic fluorine that requires 1681, that's alright, that requires 1681 kilojoules. So what type of ion are we making? If we're requiring energy, are we adding energy or removing energy?
Adding energy.
Adding energy. So what does that do to electrons?
It adds another side.
It knocks them off. It removes them, right? I think that's what I heard under the mumblings. Yeah. Okay, thank you. Okay? It removes them. So I want to write an equation for the ionization, for the removal of an electron from fluorine. Well, I'm going to start with fluorine. Okay, and it's a gas. You don't need to have that, but plus, you can either just say energy, or in this case, the 1681 .0 kilojoules, and it's per mole, right? Yeah, per mole. And what's that going to make?
Fluorine ion plus
The fluorine ion, what's the fluorine ion going to be, since we're knocking an electron off? F plus. It's still going to be a gas, plus what?
Electron.
Plus the electron. Remember, just like in math, this is why you learn things in math, so you can apply it to a real subject. When you have a plus sign, that means you have two separate terms. They're not together. Here, the cation and the electron are together. It's one neutral atom. You put energy and you're separating the two from each other. This would be the equation for the ionization of any element. The only thing that would be different is how much energy you had to add. Okay? You just have the neutral atom, add energy, you break the electron free. Okay? Did we get that right? Yeah. I mean, technically that should be an easy money point. So we go and we look at the response. Whoops. Okay? So here here's the actual scoring rubric, okay? And they didn't, notice they didn't put energy into it, they just had, that's all right, just keep it mainly on there. Okay, so, account for the fact that the first ionization energy of fluorine is greater than the atomic, greater than that of atomic oxygen. And notice this part, you must discuss both atoms. Okay? So who wants to answer that one? Read what you have.
Okay.
Teachers and students, please be aware they are working on a fire alarm system and it may go off. Please disregard.
Yeah. Okay, Mark, go ahead.
I said the ionization energy of fluorine compared to oxygen is greater because fluorine has one more proton. This proton leads to electrons being held more tightly, which increases stability.
Okay? 90% correct. You didn't say anything wrong.
The orbitals?
Yes. What one other thing does he need to say?
They're the same distance away from the nucleus.
Both fluorine and oxygen's outermost electrons are in the
2p sub.
2p sublevel. However, then you go into his answer. Fluorine has more protons than oxygen. Therefore, the electron cloud pulled it more tightly. So that whole last part was perfect and it said everything it needed to say. You just need to say where the electrons are coming from. And notice the rubric. In both cases, the electron is removed from the same energy level. That has to be clarified at the beginning. But fluorine has greater effective nuclear charge. What does that mean? More protons. But if you want to be fancy and impress AP readers, you use the term effective nuclear charge rather than more protons. But if you say more protons, it's 100% correct. Due to one more proton in its nucleus, the electrons are held more tightly and thus takes more energy to remove, which is almost word for word what Amar said. Okay? So what I'm trying to do is get you, it's one thing to understand the concept, it's another thing to be able to put it clearly and concisely into words to answer the question. I'm trying to get you to understand the phrases that you need to use to have proper verbiage to get full credit. Okay? So just kind of stare at that, soak it in. Become one with AP. All right, next question. This was tricky for many, many kids on this year. Okay, 2009. What are you guys, what, 6, 7 years old, 2009? Predict whether the first ionization energy of atomic xenon is greater than, less than, or equal to the first ionization of fluorine. Okay? Why is this tricky? Because xenon's a noble gas. And we automatically think that noble gas, they're just going to be impossible to remove an electron from wherever it is. But the reality is the noble gas only has the highest ionization energy in any given period. Whenever you go from one row to down to the next, there's always that big drop. If you go, you don't have to worry about trying to get on this one, but at home, what we're doing is looking at the periodic table, and if you look at fluorine versus xenon, fluorine's outermost electrons in the 2p. Xenon's outermost electrons in the 1, 2, 3, 4, 5p. 5p is going to be way farther away from the nucleus, much less tightly held than the 2p. So the noble gas being the hardest one is only true in the same row, the same period on the periodic table, when you're comparing electrons in the same energy level. Anytime you drop down, remember in this exciting, descriptive graph that we looked at, when you look at this, Notice again the big drop off. So here's nitrogen, oxygen, fluorine. Here's xenon down here. There's always, when you go from the noble gas, then there's a big drop down. So the noble gases, the ionization energy is decreasing as well. We good? So noble gas only in the same row. When I got the books back on this year on these students, it was almost everybody was wanting to put xenon because of the noble gas. So the first ionization energy of xenon should be less than that of fluorine to ionize a fluorine and electron. Notice again, we're talking about where the electrons are being removed from. Removed from the 2p orbital to ionize is from a 5p orbital. 5p is higher energy, is farther from the nucleus, hence it takes less energy to remove it. Very, 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 very important. You put which sublevels the electrons are being removed from in a discussion of ionization energies. And again, y'all, this is all explains why atoms react the way they do, why some things react faster than others, why some things react with one another and other things don't. If it has a high ionization energy, that means that the electron is held tightly, it's not going to be super reactive. If it has a low ionization energy, that means it loses electrons readily. All chemical bonding is all about electrons, so if it loses electrons readily, it reacts very readily. And that's what we're trying to study here in chemistry, is trying to figure out why things react, how do they react, how does the world go around. Okay? All right. That was A, B, and C. That's 2002, 2008. Is that all we had to do on that one? Yeah. So the next one's 2009. Consider the two chemical species. I like that word species. That's better than things. Okay? Write the electron configuration of each species. So what's going to be the difference between S and S2 minus?
S2 minus S2 minus.
Okay, so the mumble, for those of you watching online, the mumble said the S2 minus has 2 more electrons. Okay? So we take sulfur. How many electrons does sulfur have? 16, right? And based on where it is on the periodic table, we know its last electrons are going to go into which sublevel?
3p.
The 3p, and there's going to be how many in the 3p?
4.
4. Does everybody understand how to see that on the periodic table? It's on the 3rd row, so I know it's a 3rd energy level. It's in that P section, and it's the 4th column over, so 3p4. So that's where I need to go to. 1s2, 2s2, 2p6, 3s2, 3p4. Notice these are going to add up as 10, 16. So what's the only difference then on S2 minus?
2 more electrons.
It's going to be 3p6, which is isoelectronic with argon. You know why you know why I only tell bad chemistry jokes?
Why?
Because all the good ones are gone.
That's pretty good.
Oh, man, it's a Thursday. Here we go. All right. So, nice and easy. I'll be a stand-up comic in my next life.
Why not do it now?
Yeah, in other words, Quit teaching. Explain why the radius of S2 minus is larger than the radius of S atom. In a nutshell, what's the answer?
Electron repulsion.
More electron repulsions, okay? But now we just have to put that into clear, concise. So who wants to read their answer? How about you looked at me? Read it loud enough for the mirror on the video.
The radius of the S minus 2 ion is larger than the radius of the S atom, as it is an anion. Due to the gaining of electrons, there are more electron-to-electron repulsions, causing the electrons to spread further apart.
Okay? That's, well, I mean, I don't have any critique. Anybody have any critique of that one? That's pretty good. Okay? Do we just need to read it one more time for you guys to maybe reword yours? Read it one more time loudly.
The radius of the S minus 2 ion is larger than the radius of the S atom, as it is an anion. Due to the gaining of electrons, there are more electron-to-electron repulsions, causing the electrons to spread further apart.
Okay? Pretty close to perfect. Okay? Let's see how close we got to AP. Now, they did mention the nuclear charge is the same. Nuclear charge meaning protons. Okay, so since it's a proton to electron attraction, probably wouldn't hurt to say that. But the 8 valence electrons of sulfide experience a greater amount of electron-electron repulsions than do 6 valence electrons in the neutral sulfur. This extra repulsion increases the average distance, which what you said they cause them to spread apart. Okay, so the electron cloud around the sulfide ion has a greater radius. Now, this is a 1-point question. As an AP reader, if I'm reading this, you only have to be 51% correct to get your point. You don't get half a point, you don't get partial credit. You only have to be 51% correct. So if you had left off the nuclear charge but said everything else, you still would have gotten your 1 point. Okay? Does anybody have any questions on that one? This is the one where you're supposed to watch the video. Who watched the video? Well, I'm not even going to ask that. Okay? What are our 3 types of magnetism?
Ferromagnetism, paramagnetic, and diamagnetic.
Okay? I'm hearing one person and everybody else. Y'all, I sent that out. 9 minutes. 9-minute video.
I'll watch it tonight for you, Mr. Hobbs.
Okay.
I was there.
Yeah.
Yeah, I was 7th period. Tricks.
When they asked the question in class about this in 7th period yesterday, I said, ooh, I probably didn't go over this in the other class. I probably need to record it because I was thinking about you and your well-being.
I appreciate that. We appreciate that.
Yeah, I appreciate it so much. You just ignore it completely. Despite my in the classroom explanation, this is really good stuff. You really just need to watch this 9 minutes. And I specifically said 1st and 2nd period students as well as full-time virtual. All right. So, Zoe, what are 3 types of magnetism?
Ferromagnetism, paramagnetism, and diamagnetism.
Ferromagnetism, paramagnetism, and diamagnetism. Okay? I'm just going to give you a real brief explanation of this, and you can go home and watch that 9-minute video and get a much more full explanation. Okay? Ferromagnet, what does this word sound like?
Iron.
Iron, ferro. Okay? Iron magnetism. Iron is by far the most common magnet. Okay? These are your permanent magnets. Now, why are we talking about magnets when we're talking about electrons? Because one of the fascinating things about chemistry and about the world is that all magnetism has to do with that electron spin. Remember, some are spinning clockwise, some spinning counterclockwise. Okay? It's a 50-50 proposition. So if I have a piece of iron, when we look at its electron configuration, it stops at 3d6. Okay? 3d6 right here. Okay? So it has 4 unpaired electrons. Those 4 unpaired electrons in half the atoms are going to be going the clockwise spin, and the other half they're going to be going counterclockwise spin. Half of them are going to be up arrows, half of them are going to be down arrows. It's just, and they're going to be mixed evenly throughout. So there's no magnetism. But you put a piece of iron into a magnetic field, and all of the ones with the plus arrow, up arrows, they all align on this end. And all the ones with the down arrows all align then this. Now I'm just representing 2, but I mean there's bazillions of each one, but all the ups go to one end, and all the ones that with electrons the down spin are all going to the other end. That creates my north and my south poles, based upon electron spins. Now what's unique about these is that once you take it out of the magnetic field, they stay. They don't migrate back. And so as a result, it's a permanent magnet. Really only iron is the most common. Cobalt and nickel, I think, can do that. Some of your rare earth metals, especially neodymium, form a very strong permanent magnet. Okay? But not many substances are permanent magnets. Okay? Now, paramagnetism, they're affected by a magnetic field. You put them into a magnetic field, and they'll be affected by it, but as soon as you take it out of the electric field, then the magnetism goes away. So, okay? And the way we can know that, it must have at least one unpaired electron. At least one. You can have 2, 3, 4, whatever. Okay? So what do you think diamagnetic is?
No.
Say that again.
No, not attracted to a magnetic field.
Not attracted to a magnet. No, it's not that. Some even say it's slightly repelled by magnetic field instead of attracted to it. Now, based upon how we've been going here, what do you think, what type of elements are going to be diamagnetic?
Ones with full sublevels.
Filled sublevels, why? In a filled sublevel, what don't we have? Unpaired electrons. No unpaired electrons. So which groups have no unpaired electrons?
2, 10, 18.
2, 12, and 18. Field S, field P, field D. Or in that order, field S, field D, field P. Be diamagnetic. Okay? Now, if you don't know this, this one is tricky to answer because I would tend to want to say, well, the S2 minus has got a charge on it. It's the one that's going to be attracted to the magnetic field. Now, it would be attracted in an electric field, but the electric charge and magnetic charges don't overlap. So, which one of these has unpaired electrons? S or S2 minus?
S.
S. Okay? So what do we need to say in the answer?
S squeeze has no unpaired
Okay, Zoe, you gotta say it loud enough.
S because it has unpaired electrons.
Making it
Paramagnetic.
paramagnetic, okay? The S atom has 2 unpaired electrons, causing it to be paramagnetic and attracted to a magnetic field, whereas S2 minus has no unpaired electrons, causing it to be diamagnetic and not attracted to a magnet. Sulfur would be attracted to the magnetic field. Sulfur has two unpaired p electrons, results in a net magnetic moment for the atom. The net, so you can, net magnetic moment, that's not a term we were comfortable with or would use, making it paramagnetic. Okay, you can substitute that in. This net magnetic moment would interact with the external magnetic field, causing a net attraction to the field. Okay, all you gotta say on this is making it paramagnetic, so it would be attracted to a magnetic field. You do not have to define paramagnetic if you're using it correctly. You, in a sense, are defining it by saying it's got two unpaired electrons, making it paramagnetic. Okay? And attracted to the magnetic field. Whereas the sulfide ion would not be attracted because all electrons are paired, meaning that their individual magnetic moments would cancel each other out, making it diamagnetic. Okay? So don't worry about the whole idea of magnetic moments. Moment is a physics term, but just know your terms paramagnetic, diamagnetic. They're never going to ask you anything about paramagnetism because it's just permanent. And there's only, you just have to memorize, and they're trying not to do that. So this is just a question about magnetism. All right. So you got S2 minus is isoelectronic with argon. So what does that mean?
It has the same.
Same electron configuration as, right? So they both have 18 electrons. Which one's going to be harder to take an electron from? Argon. Why? More protons, fancier words. It's got a greater effective nuclear charge. Okay? Now, what do you think you need to state in your answer? What two things that we just mentioned?
It has the same electrons.
Okay? What about sublevel?
Which they both have their outer limits the same.
Okay, so they have the same they have the same electron configuration, the same number of electrons. Okay? So their electron configurations are the same. Okay? That's really what isoelectronic is telling us, but I would restate that in my response. Both S2 minus and argon can have 18 electrons or have the same electron, outer shell electron configuration. Argon has more protons, or argon has a greater effective nuclear charge due to more protons than S2 minus. As a result, the electrons will be held more tightly and harder to remove. Valence electron of the sulfide is less attracted to the nucleus, charge plus 16, than is a valence electron in the argon atom, plus 18. So there's, what are they saying right here? More protons, a greater effective nuclear charge. Okay? I can't believe that they just put it like this. I would have expected the rubric to have the effective nuclear charge phrase in it. Okay? Are y'all seeing what's required, what you need to say to answer these questions? Okay? All right. Now this one we're going to get into more later. I don't know if it was this class or the other class that talked about this. But talking about atomic orbitals. And of the atomic orbitals that we know of, which ones are at 90 degrees?
The P.
Okay? Zoe said the P. Well, how are the P orbitals oriented in terms of 90 degrees? Okay, I just put them all up from yesterday, but where are 3 P orbitals, or how are they oriented?
Like a cross.
Say that again so I can hear you. on the X, Y, and Z axis. And the angle between X, Y, and Z is always 90 degrees. Okay? So if you have a 90-degree bond angle, it's going to be P sublevel. Okay? So if you want to, on your paper, on your answer sheet, whatever, I would maybe make a notation of that. 90 degrees is always going to be a P sublevel. We're going to learn in the next unit about this thing called hybridization, that the electrons, when they bond, they actually form molecular orbitals. They change where the orbitals are when they bond, okay? Which is going to change the angles, and we're going to learn all about shapes and angles. But the only one that's going to be 90 degrees is just a normal p orbital, okay? Three p orbitals mutually perpendicular, i.e. at 90 degrees to one another. Pretty straightforward. All right, this is flashback. Okay, so you got two types of intermolecular forces in H2S and H2O. Okay? Compare the London. How do London dispersion forces, what do they vary with?
Electron cloud size.
The size of the electron cloud, right? Where the bigger electron cloud is more, what's the key AP word?
Polarizable.
Polarizable. Okay? So, how does H2S's electron cloud compare to H2O's?
It's larger.
It's larger, therefore its London forces are going to be greater because the H2S has a larger electron cloud, making it more polarizable, giving it stronger LDS. Okay? The strength of London force is greater than that of the London water. The electron cloud has more electrons and is thus more polarizable than the electron cloud of H2O. And I would finish that by saying, you know, well, it already says greater London forces in the beginning. All right? But now, that was the first part. That was comparing the London forces. But now it says, compare the strength of the dipole-dipole forces in H2S to the strength of the dipole-dipole forces in water. What do we call the dipole-dipole forces in water?
Hydrogen bonds.
Hydrogen bonds. Are they going to be stronger or weaker than the H2S? Stronger. What's the key difference between the two?
More polar.
More polar. Why is it more polar? What determines the polarity? The electronegativity. Remember the attraction for that shared pair of electrons. Oxygen being one of the big four, phone call. Oxygen, we know, is way more electronegative than sulfur. So therefore, the dipole-dipole forces are going to be much greater in water than in H2S. So you have H2S having stronger LDFs, but the water having much stronger dipole-dipole, including hydrogen bonds. So those hydrogen bonds way overcompensate the LDFs. H2S is a gas at room temperature, smells like rotten eggs. H2O is a liquid until 100 degrees. Okay? Telling me that the dipole-dipole attractions are pretty significant. Okay, the first two lines here are a little bit redundant. The strength of the dipole force is weaker than that, the net dipole moment. And by the way, whenever you see this word, dipole moment, that's a measure, it's a quantitative measure of a molecule's polarity. Okay, so in other words, they put a number on it, and there's a way to measure it. Okay? We're never going to have to measure it, but whenever you see dipole moment, that means you translate that to polar. So you can really say the H2S molecule is less polar than water. Okay? This results from a lesser polarity of H bond compared with the HO bonds. S is less electronegative than oxygen. So you could even throw in a discussion of hydrogen bonds in there. Water has, you know, hydrogen bonds, which is a special type of dipole-dipole, making it have much stronger attractions than the much weaker dipole-dipole attractions of S. Now, but I think this is important here. that you mention that. Okay? Because that's the key difference between H2S and H2O in terms of dipole-dipole. Okay, you good with all that? All right. Now, I really want to go over 16, 17, 18, and 19, but I think I'm going to wait until tomorrow. I don't know, we might do a lab tomorrow, till Monday to go over those four. I gave you the two PES practice questions as well, okay? But I want us to really spend some time in the Princeton Review on the multiple choice, okay? So in the Princeton Review, the very first unit, okay, going to start on page 77 in your Princeton Review. And all of these multiple choice questions, there were 19 of them, seem good, as well as the 4 free response, 2 of them being PES questions. So I recommend, well, let's just do it. Let's take time and, whose is this one if I just grab it?
Paris gave it to me.
It was here. Nate, is this the one that Nate's supposed to be giving to Nathan?
I think they're the same one. Mine's just blue.
Did you order it way back when?
77, I think.
Yeah. And it still hadn't come? Wow. Princeton Review 2021, the required review. Okay? And that was in the syllabus. Amy, you don't have one yet, Ian? All right, if you don't have one, get your phone, take a picture. Okay? Take a picture before they start answering it. I want, all of the 19 multiple choice questions and the 4 free response. Okay? Y'all need to get one. Okay, I've been telling you since August.